Okay, let's talk about sketching real polynomials, graphs of real polynomials today. Okay, this isn't going to be, when I write graphing here, the graphs are not going to look perfect or anything like that, but it should give you an idea what the graph ends up looking like. The first thing we want to consider when we're talking about graphing a real polynomial, again, real polynomials only is what we're considering here. So that means in any of my polynomials, all the coefficients are real numbers. Okay, let's talk about the end behavior of a polynomial. Suppose I have a real polynomial, say p of x, a sub n, x to the n, a sub plus a sub n minus 1, x to the n minus 1, so on and so forth, all the way down to the constant term a naught. I assume that the leading term, a sub n, x to the n, has what that leading coefficient there is not 0. Otherwise, we probably wouldn't write this at all. Okay, what is the end behavior of a graph? The end behavior of a graph, like y equals p of x, is the behavior of the graph as x approaches plus or minus infinity. Obviously, there's no end to the real numbers, so maybe this is kind of poor language, but it's somewhat suggestive here. Okay, so we're thinking about what the graph kind of looks like as x approaches plus or minus infinity. Now here's my claim. If you're dealing with a polynomial, the end behavior of a polynomial when you graph it is completely determined by the leading monomial term, right? The leading term, okay? So in this particular case, I would be determined by y equals a sub n x to the n power. Now we're going to take a couple examples here, and we're actually going to look at the graphs in a little while. But right now, just imagine here, y equals p of x equals negative 2x cubed plus 2x squared plus 2x minus 2. The leading term would be minus 2x cubed. Okay? Now, my claim, what this function basically looks like as x gets large in absolute value is completely determined by that dominant term, that highest degree term, the negative 2x cubed. Now, if you remember, we actually graphed monomial power functions and monomial functions in an earlier video. You should be able to tell me what that would look like anyways. If I go y equals negative 2x cubed, what would that graph look like? Okay? Alrighty? Well, we're going to look at it again if you've forgotten here. And then we're going to take a second example here. Y equals x to the fourth plus x cubed minus x minus 1. Okay? So I claim in the long run, as x approaches plus or minus infinity, it's looking like y equals x to the fourth. Do you remember what that looks like? Okay? Well, again, we'll look at this in greater depth here when we put all the pieces together in graphing real polynomials. Let's consider something else when we're talking about the graph of a real polynomial here. We're going to talk about the real zeros and turning points. Real zeros, you remember what a zero of a polynomial is, right? It's a value for which when you evaluate the polynomial, you get 0 as a result, right? You plug in that value of x and you get 0 coming out of the polynomial, right? Okay, if you think about when we're graphing here, we're just going to be graphing in the Cartesian plane, the regular xy plane. So that means x and y are going to have to be what? Real numbers here. Okay, so when we talk about the zeros of a polynomial, all we're going to be concerned with as far as the graph go are the real zeros of a real polynomial p of x, okay? So even a real polynomial may have what? Complex zeros. We're not going to be concerned with those because those don't appear on the real number line. If you were going to do the whole thing, you'd actually need 4 dimensions if you were going to start talking about values of polynomials at complex values, okay? And we don't have that many dimensions available to us here. But if you go ahead and think about this, wait, the real zeros of a real polynomial are really the x-intercepts of the graph, y equals p of x, right? Because what? What is an x-intercept? It's a point on the graph where it crosses the what? X-axis. And any point on the x-axis has what? Y equal to 0, y equal to 0. So you'd be looking at 0 equals p of x. Solutions to that are what? zeros of the polynomial. Again, now we're only concerned with real zeros, though. Okay? Now, from the fundamental theorem of algebra, what did the fundamental theorem of algebra say? Any polynomial, real or complex, the number of zeros is equal to what? The degree of the polynomial. It does say that you might have to go to the complex numbers for that to occur, right, to find all the zeros, and that would be counting multiplicity. Since we're not worried about complex or imaginary zeros today, only real ones, then what we could say that the fundamental theorem of algebra implies is a real polynomial of degree n could have at most n real zeros, right? The number of real zeros might be equal to the degree, but it might be less too, right? If it has some complex zeros, imaginary zeros, if you will. Okay, so it could have at most n x-intercepts. Okay, now here's some things. We'll see why this actually holds in a little bit here. But if a real zero of the real polynomial p of x has odd multiplicity, remember how we were talking about how multiplicity eventually come into play here? If a real zero has odd multiplicity, then I claim the graph actually crosses the x-axis at the zero. So odd multiplicity, it crosses. However, if a real zero of a real polynomial has even multiplicity, then the graph bounces off the x-axis at that zero. Some people, like John Grimma there, just say touches. I like a more active verb here. I imagine moving along the curve, and I claim bounces is probably more active there. So it bounces off the x-axis at the zero. Again, we're going to see some of this coming into play as we go along here. Okay, we'll be looking at some examples, but you need to remember these. Okay, shouldn't be too bad once we get used to it. Okay, turning points. You've actually seen this concept before. You remember local maxima, local minima. We also called those local extrema. Okay, in this context, people will often call them turning points of a graph. Okay, so those are the local maxima or minima, local extrema. These are places, this is where the language comes from. These are places where the graph turns from this should be from, not form, from increasing to decreasing or vice versa, okay? So where it turns from increasing to decreasing or decreasing to increasing, okay? Alrighty. Now, this is just a fact that we can prove once we get to Calc 1 here. A real polynomial of degree n can have at most n minus 1 turning points. Okay? So the maximum number of possible turning points for a graph can be what? At most 1 less than the degree. Okay? That's for a real polynomial. All right. Now, when we go through and we're graphing these things, some things we want to remember to make our graphs look, decent, even if they don't look great. The graph of a polynomial is continuous. Do you remember what that meant? That meant you could graph the polynomial y equals p of x or whatever without lifting your pen from the paper. So that means that there's no jumps in the graph or anything. There's no holes or anything like that. So you can draw the graph without lifting your pen from the paper. Another thing to remember to try to make your graphs look good is that the graph of a polynomial is smooth. Now this has a very fancy and well-defined meaning in Calc 1 here called differentiability. But we'll just think of it this way. It's smooth. It has no corners. Okay, so don't do this. Don't draw your graph with something like that. That's a corner there. Graphs are always, polynomials are always smooth. Okay? Okay, well that didn't look very smooth there, but you get the idea. All right? All right, there we go. Now let's talk about graphing some of these things in behavior. I'm going to start out here a little bit like I'll give on the exam when it comes here. Let's start out like this thing, okay? This was that first polynomial I mentioned, that first example 1 here. So that's really this guy. Okay, so I got it written out there. Let's go ahead and let's talk first about the leading term. Okay, what would be the leading term? And I'm going to include y equals, so I guess I'm technically doing a little more than the leading term, but y equals negative 2x cubed. So if this is written in its descending order like it should be, right, it'll be the first term you run into here. Negative 2x cubed in this case. Okay, now what is the end behavior? What does that look like? Well, can you imagine actually graphing this? Okay, imagine x is approaching minus infinity. So we're seeing what happens in the extreme as x approaches minus infinity. So imagine x is a really large number in absolute value, but it has a negative sign. Okay, if I take a really large negative number and cube it, what do I get? I get a negative number that's large in absolute value, right? Okay, all right. And if I multiply that by negative 2, I get a number which is what? Positive with a large absolute value. So that means it's coming up like this. If I go to the other end where x is positive, imagine taking a large positive number and cubing it and then multiplying that result by negative 2. I would get a number that's large in absolute value, but it is actually a negative number, okay? So the graph of this thing would look like this, okay? All right? Now I claim the graph of this thing is going to look like this, except for what's going to, or more or less like this, is it's going to have the same end behavior, but when you get near the origin here, it might be bobbing around up a little bit. So I might be doing something like this, you know, bobbing around. Okay? Well, this has too many turning points for this, but anyway, that's the idea. But it has the same basic end behavior as just the leading or dominant term here. Okay, let's just give a quick description here of this end behavior for this leading term. What would that be? We'd be going from what? The upper left, right? The upper left. And as you come this way, for increasing values of x, we would end what? Lower right, okay? Lower right. For people that know about quadrants here, 1, 2, 3, 4, the positive direction in math is counterclockwise. You would be starting from what? The second quadrant and ending in the fourth quadrant. That would be another way of thinking about it. Okay? Let's give a real factorization of the polynomial. Okay, so here's my p of x. Now I say real factorization because we know all polynomials will factor in terms of their zeros, but I'm not interested in any zeros that have what? Complex numbers in. You know, so let's go ahead and see if we can do this though. These zeros will give us an idea of what this graph looks like when we combine it with end behavior. Okay, first thing I notice here is I can factor a negative 2 out of all the terms here. And I'd prefer to factor out the negative as well here. You notice this is a monic polynomial inside parentheses. Now, that may be a little bit easier to factor then. I'm noticing here, hey, wait a minute, I think we can actually use factoring by grouping here. Okay, let's factor out a minus, there's actually a 1 there. Okay, you guys notice that we have what here? You have a common factor being x minus 1. So in a situation like this, you might try factoring by grouping. With that common factor of x minus 1, we could factor this out. So we can factor out an x minus 1. And now, can you factor that? Can you see that's actually a difference of squares? It's x plus 1 times x minus 1. And then I have that extra factor, x minus 1. So my p of x actually factors this way. Let's write it a little more compactly with exponential notation. So I've got this. Okay, so there, I factored it as much as I could here. Not interested in anything but a real factorization. Okay, we'll consider that when we do the second example also. Okay, good. Now, I'm going to show you here what we're going to do. You'll have this little table to fill out. Now, what are the real zeros? I should put this in here. These are real zeros, right? Not interested in complex ones because we're interested in graphing here. Okay, what are the real zeros here? Okay, negative 1 is a 0. What's another one? 1. Okay, the factor -2 doesn't lead to any zeros here. Okay, what's the multiplicity of -1? Well, what power actually appears here? How many times does that factor appear? Just once. So we called that a simple zero, didn't we? How about the 1, though? The x minus 1 appears twice. That is multiplicity 2. Now, let's go ahead. Do you remember? It says what? If it's odd multiplicity, then it does what? It crosses the x-axis. If it's even multiplicity, what does it do? It bounces. Okay? Now, I'm going to give a rough graph. Again, this is just a sketch. Nobody claims it looks great or anything. I'm just going to give you an idea what this would look like. So we'll have our xy axes. Okay, we've got zeros here at what? Those are really -1 and 1. Those are x-intercepts, right? Now let's bring our end behavior into it. The end behavior is like this. So it's going from what? Upper left to lower right. So that means it's coming in like this here. Okay? And it should end down here like that. Does that make sense? Okay? Now, what does it do here? It comes here. And remember, this is an x-intercept, so it's going to go like this. And then what's going to happen? It says it's going to cross here. So it crosses through. Okay? And then it's got to go what through? It's got to go through here, but it's going to do what? It's going to bounce when it gets here. Boing. Like that. Okay? So this is a rough idea of what my graph looks like. Now, something else you might do, just to make the graph look a little bit better, I could have let x equals 0 and got what? The y-intercept was -2 here. Okay, it didn't really look that good. I probably should have done that. But this gives you a general idea of the graph would look like. Okay, so this is my graph of y equals -2 x cubed plus 2x squared plus 2x minus 2. Okay, kind of rough there. How many turning points does this have? Oh, by the way, we don't know how low this turning point is. Do you see we have a turning point down here? We don't know how low that is or the coordinates of that point. That's going to take some Calc 1. So that's in your future if you're going to have Calc 1. But we should. It looks like how many turning points on this one? 1, 2. This would be a local minimum over here somewhere. May not be on the y-axis. And we have another turning point right here. Okay? So total number of turning points. What's the maximum number of turning points this could have had? 3 minus 1. 2, right? The degree minus 1. So it could have had at most 2 turning points, and that's it actually. It does have 2 turning points. Okay? So let's go ahead and compare this with the actual graph I took from Desmos. So you get that idea what we're supposed to be looking at here. And it's the red one here. This is the actual graph. Notice that we had what? A turning point down here. I didn't know how to calculate that, right? Actually, I do know, but I can't tell you guys right now. Okay? And then we've got, my graph looks pretty good, doesn't it? Okay? What's this blue one, by the way? This blue one is what? The leading term. That's the graph of the leading term. Notice that these have the same end behavior. That was the idea, right? It's going from upper left to lower right. And so is the orange graph, the one we were interested in. Okay? Now you can always do these and you can follow these on and graph these on Desmos yourself. Okay? All right. All right, let's do another example here, that second example. And then you should be able to tackle a lot of these problems. Our second example was this one. Example 2. Okay? I don't have a table written out on this one, so I guess I'll just do it by hand here. But this is our function. Okay. Okay, let's do what's the leading term? Okay, and I'm going to go y equals again. Just pick that off there, that's x to the 4th. Do you remember what that looks like? Okay, yeah, it looks kind of parabolic, doesn't it? So it's going to be going from what? The upper left to the upper right. Okay? So that means when we graph this thing, it's going to look like that also. Well, it's going to do this and maybe bounce around a little bit like that or something. Okay? But it's going to look kind of like this in the long run. Okay? All right. What's the next thing we want to do here? We've got to do some factorization. Let's see if we can factor this thing. Okay? Now, if you had a hard time factoring this, one of the things you might do is, well, I'd always try factoring by grouping, but you might look for what? You might look for possible rational zeros and try those one at a time. Remember, like we did in the previous video. Okay? I think this one actually factors pretty easily here. Let me maybe do this in greater depth here for the factoring by grouping, so nobody gets confused here. Now I have a subtraction here. Now don't forget what you're going to need to do is actually distribute that negative sign through these. So just double check and make sure you have the right terms here. Sometimes students make errors that way. Okay, negative x minus 1. Check. Everything looks good. Now, do you see I could factor out an x cubed here? Okay, and that would be what? X plus 1 here. Now, don't get confused here. This has an x plus 1 here. If I want to stick a factor in there to get a common factor between these two, remember I could stick a 1 in there. So this actually factors as x cubed minus 1 times x plus 1. Okay? Now, here's something I want to throw in here. Remember, we're only looking for real factorizations. Okay, we're only looking for real factorizations. I claim this is going to have to factor here. Okay, there's no such thing as a real polynomial of odd degree that can't factor in the reals. Okay, we would say every real polynomial of odd degree is reducible. Okay, that means it's factorable. Okay, do you understand why? Well, because x cubed minus 1 is acting like this. What is x cubed acting like? It's going from the lower left to the upper right. Since the graph is continuous, it's got to cross somewhere. It's going to have a 0. It's going to have a real 0 here. This guy, I mean. Okay? Now let's go ahead. We got to consider factoring x cubed minus 1. Now you remember, so let's factor x cubed minus 1. We're ready? All right. Remember that these factor in terms of their zeros. Can you think of a 0 of that polynomial right off? I can. What's a 0 of that thing? How about 1? Yes. Okay. X equals 1. I claim 1 is a 0 of that polynomial above. Okay. Let's just go ahead and a synthetic evaluation if you want to double check that, but we can see we're going to get a quotient that's important here. How does a synthetic evaluation go? 1x cubed, 0x squared, 0x minus 1. Okay, bring it down, multiply. Don't forget to add 1 to 1 is 1. Add 1 to 1 is, and we get 0. Guess what? That polynomial x cubed minus 1 evaluated at 1. Okay? 1 cubed minus 1 is indeed 0 here. What does this represent? Okay, that represents a quotient, right? Do you see that's going to be what? A second degree polynomial. I've got x minus 1 here. What are the coefficients? It's going to be what? 1x squared plus x plus 1. Okay, so now square. Okay, we've got x plus 1 there as well. All right, let's see what happened. All right, sorry there for a minute. I had a technical glitch. Anyways, so our polynomial has this factorization. And then lastly, we want to consider that. Okay, does this have a real factorization? Well, remember, all polynomials factor in terms of their zeros. If I was to take this polynomial, set it to 0 and solve, I would try factorization in my head, try plus or minus 1 and stuff like that. It's not going to work. Try the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Oops, you guys notice right here? That is a negative number. That's in fact negative 3. This only has what? Imaginary zeros. Now this does factor in terms of those zeros there, but they're imaginary, so they're of no concern to me. Okay, so they're of no concern to me. So I've got its complete real factorization now. Okay, I've got its complete real factorization. So let's go ahead and make out our table here. Okay, we've got the zeros, real zeros, multiplicity, and then behavior, cross or bounce, right? Okay, let's do them in order here. If I take that factor, set it to 0, and solve, I would get -1. If I took this factor, set it to 0, and solved, I would get what? 1. If I take this factor and set it to 0 and solve, I get complex numbers, so that doesn't even come into play. The multiplicity on both of these is what? 1. Since 1 is an odd number, they both what? I get a cross. Okay, a cross in both places here. Now let's give a rough sketch of what this thing would look like then. Okay. Just to show you here, let's see. Here it is. Remember how we had what? Our end behavior is x to the 4th. Okay. This thing crosses at what? -1 and 1. Okay. And it must come down like this. And then it must go back up like this. Okay. Now in here, I can't really tell what's happening since I don't have Calc 1 at my disposal here. But, okay, so if you went like this, that would be okay. That would give it only one, what? Only one turning point, but it may be that it has more than that, okay? We can't really tell right now. But so this is a pretty rough sketch on this particular problem, okay? This is kind of a rough sketch on this one, okay? This complex factor is playing a little bit of a role. It's not giving us any zeros, but let me go ahead and show you the graph of the actual polynomial. It's actually in green here. Let's focus. It's actually in green, okay? It does, this actually, that is not a turning point, okay? But this is a turning point right there. This is y equals x to the 4th. See how, again, how they have the same end behavior, but this one's just a little bit messed up here, okay? So I guess my drawing isn't too bad, okay? It wasn't too bad there, okay? Well, this should give you an idea of what you guys need to do when it comes to the exam. I'll be asking you to draw rough graphs of real polynomials and where, you know, the real zeros, the x-intercepts that is, where it crosses or it bounces, and show, you know, how many possible turning points and the end behavior and stuff. So it shouldn't be too bad there. Okay.